Assalamualaikum warahmatullahi wabarakatuh. Today we will present about DC-DC boost converter for project assignment control principle. So thank you for the lecturer, Dr. Hafiz bin Sagawi. So I will intro my group. First, Nagawali, second Yasigi and Muhammad Ani Aklan, and I, Muhammad Irfan Anjahan bin Mukhtar. So we from 2BE section 1 stroke 1. So uh, go to introduction. I will explain. So DC-DC boost converter is one of the simplest type of which mode converter. A DC-DC boost converter, also known as a step-up converter, which capable of producing an output voltage that is higher than the input voltage. So figure 1 show the DC-DC converter topology for the boost. Uh, so this boost converter are operated into mode. So mode 1 and mode 2. For mode 1, the MOSFET is one state, allowing the input voltage to store energy into the inductor, while turn turn the diode of sync its positive terminal is grounded. So for mode 2, the MOSFET is off state. The diode is turned on, and the energy from the inductor is released to the load to maintain the load current. So this is figure 2 equivalent boost converter in circuit for mode 1. So figure 3 equivalent boost converter circuit for mode 2. So for the problem statement for this project, the issue that need to be focused as rapid testing, non-linearity, and calculation problem have to be solved repeatedly until the work it reaches of tolerable result. So the book's converter circuit was simulated using multi-sim software. Therefore, by using MATLAB software, where it help to analysis the output voltage transit response, such as rise time, overshoot time, and settling time. So for the objectives result, objective project, uh, 3 point for the objective, to study boost converter topologies and analyze the stability for each equivalent circuit demoted as mode 1 and mode 2. To derive the state space SS model and state space average SSA model of the converter. So to study the difference between of output loop and closed loop in system of boost converter. So that's all for me. Thank
Hi, my name is Muhammad Ani. So I will present about methodology. So this is a DC to DC converter topology for the boost. The well-known circuit for the DC to DC converter are the boost converter. The duty cycle value was used to calculate the capacitance value that result in max peak to peak ripple voltage of 0.5%. Minimum value of inductor was calculated to ensure the continuous current mode of R condition. So the boost converter was designed by using the given requirement value of V out is 18 volt. Input voltage of nominal is 12 volt. Output power is 10 watt. Ripple voltage of 0.5%. Output voltage is 18 volt. Operate in continuous current mode (CCM). So we know that MOSFET has two type mode, which is on state and off state. So the red line is the current flow in the circuit. So when the MOSFET on, which is the mode 1, the component in MOSFET is closed and current will flow from power source. The red line means flow of the current. This makes voltage dropping from capacitor to output. The capacitor only makes the voltage drop at the output load voltage. The component diode back the passive back to the power source. And then this one is the second mode, which is MOSFET off. The component is in MOSFET is open and make an open circuit near the power source and shown in figure 5. So this is the open circuit because the switch is turning on. The switch turning off. So the capacitor and load resistance, the red line means flow the current. In this situation, the capacitor is in charge and the voltage will be stored to be released in the next stage in mode 1. To load resistor has to make voltage step up system a boost converter. Next, this is the operational of the boost converter circuit. Okay, when MOSFET was closed at mode 1, the inductor will start to store voltage or energy. So when MOSFET open, which is mode 2, the voltage from battery in the inductor will be used to charge the capacitor. When the MOSFET keep on switch between mode 1 and mode 2, the higher charge voltage in the resistor from the battery source will increase continuously as each cycle running. For each cycle, inductor will transfer energy to the capacitor. The capacitor voltage will increase until it reaches state of equilibrium. The function of the diode in boost converter is to block the capacitor from being discharged back to the battery source to achieve equilibrium, so that the capacitor can be only sending the current and voltage to the load voltage. In addition, the sum total of voltage from battery and also inductor is greater than the source battery for higher output. The current will be decreased, which the power is remained. There is also a very little current loss when the cycle is carrying the current loss to surrounding and source when the gate on MOSFET closed and open continuously. As the frequency increasing, the voltage charge across inductor and capacitor will increase too. In precaution, we are handling the boost. We should be alert to the current because the high current may bring damage to the engineer. So next is the state space model and equation. To apply every method for modeling mode 1 and mode 2 model operation are mode as follows. So this is the equation. This is equation for mode 1 and then this is the equation for mode 2. So this is the Gantt chart, the flow to our work. So we will not miss the work lah. Okay, thank you. That's only for me.
Result part. So first I'm going to start with the mathematical result calculation part. So from here we know that the given the value for the voltage V in will be 12 volt, V out will be 18 volt, and P out, the power out, will be 10 volt, and the Fs is the frequency will be equals to 20 kilohertz, and R will be the 0.5%. So first to calculate, do the mathematical calculations, first thing we need to find the duty ratio or the duty cycle for an output voltage of 18 volt. So from that we need to use this formula, V out over V in equals to 1 over 1 minus D. So D will be the duty ratio. So 18 divided by 12 and 1 over 1 minus d. So then we can get the d value will be equals to 0.33. And then second, we need to find for the output current. So IO will be equals to the PO. We can use the Ohm's law, that means, or the power law that you can say. PO equals to IO VO times. So then IO equals to VO over VO equals to 0.566 ampere. So then we can find the output resistor. So this resistor will be used, these are the variables that will be used in for the boost DC-DC converter later. So V out equals to I out, R out. So R out equals to V out over I out will be equals to 32.4 ohms. And then to find the inductor, we can use this formula. They will have the inductor minimum value and then the maximum value. So for the later for the stimulation part, we will use the L maximum to find for the circuit, okay, for the converter later. So L minimum will be equals to D 1 minus D RO over 2 Fs. So one substitute we can get 1.7909 times 10 power of 94 H. And then the Lm will be equals to 1.25 times by the L minimum. So we can get 2.2386 times 10 power of 94 H. Then to find the capacitor, we need to use the R resistor and also the R small r. So D over R times by the small r times by the Fs. So then we can get 1.01. That means the R actually is a repel voltage. Okay. So we can get 1.0185 times 10 power of negative 4 farad. Okay, this thing. Then we're going to see the state space derivatives, the difference between the mode 1 and then the mode 2. So this is the circuit for the equivalent boost converter circuit for mode 1. That means the MOSFET will be on condition. So this is the state space, the derivations of the state space equation. So X, this one with the differentials of the X, it will be equals to first differentiation will be equals to A 1 times, so I'm consider mode 1, so 1 in 1 to X plus B1Q. So this is the equation, the matrices, and then we substitute the values, the value for that one, the things, and then we can get the derivations. This is the state space. Based on the formula, this is the formula we use, and then we substitute the values. Okay, similar for the mode 2 also, we use the same, but remember mode 2 is the one that MOSFET will be in off condition. So the equation will be this, the state space that we obtain for mode 2. So it's a formula, and we substitute the formula and we can get the values. Okay. So the lastly, the average state space model, SSA. So the AX will be equals to A bar times by the X plus B bar U. So we consider the, just now we consider the A1 and then A2. So now we consider with the average will become the A bar. Okay, then the A bar, this is the thing, and B bar will be this, the equation, the operations. And then we substitute all the values, and with the formula, we can get the average state space model for this one. The result part, the MATLAB result for our assignment. So this is the figure, shows that figure shows the DC-DC boost converter topology in MATLAB software. So as for us, group 3, we will assign to do the DC-DC boost converter, the boost with the input of 12 and the output will be 18. So first I will show the block diagram in MATLAB. Okay, so firstly, this is the DC voltage source that we assigned is 12 volt. Then the inductor, the variables, the inductor that we choose is 2.24 with a power of negative 4 H. Then the MOSFET we choose here to show that mode 1 and mode 2, when the condition mode 1 when the MOSFET is on, and the condition mode 2 when the MOSFET is off. So we use the pulse generator to show the pulse from the MOSFET when on and off condition. So this is the period, the frequency that we set is 20,000. Then the pulse width, that means the ratio, the duty cycle or the duties ratio, that means 0.33 times by the 100% because it's 1%. Then this is the diode. Then we assign for the capacitor value will be 1.0185 with a power of -4. There for the current, we use the current measurement later to show the current measurement using the scope, the output. Then we assign the resistor value 32.4 ohms. Okay, for the output display, we use the display. We use this display to display the output voltage, and we also use the scope to show that the voltage, the waveform or the signals that come out for output voltage. Okay, this is the diagram. Then I'm going to run. Okay. So as we mentioned in question, as we asked in question that our DC, the input must be 12 volt and the output must be 18 volt. But we get is 17.96, which is nearest to the 18 volt. Okay, now I'm going to see the scope, show the scope. Okay, this is a scope. This one for the DC, for the voltage measurement for the input. So the input, the graph will be, the value will get, it's 12 volt here. And this one will be the voltage measurement. This one will be the output voltage measurement, the graph. So the output we get is 17.96 volt actually. Okay, this is the part for the Simulink. Now we will further with the slide. So this is the coding for the state space boost converter model. So this is the average state space boost converter model. So this is the coding. So we assign this one. I will show in MATLAB. Okay, so this is the coding. So the R, which is now assigned 32.4, and this one I using the formula of P equals to V, the IV. This one from the mathematical result we get just now. We used it one. The I will be 0.556 and the C capacitor 1.0185. This one we're using all from the calculation that we calculated in the under the methodology part, mathematical results calculation. And so num will be the numerator 1, denominator will be RIC, the system transfer functions to show the transfer function, and so steps SYS to show the step response graph. Okay, so when I run, okay, this is step response graph, and first we're going to see this is the SYS, that means the transfer functions, the equations. Okay, state space transfer function. So we get 1/32, this one the resistor, this one the current, and this one the capacity. Okay, now we're going to discuss about the, okay, so as in question they ask us to show the step response, to show the peak time, the overshooting, and the rise times, and also the settling time. So first we're going to say the peak response. This is the peak response. So this is the overshoot will be 30%, with the peak amplitude given 69.7, and this one the peak time will be 140 seconds. Now second we're going to see it's about the settling time. So this is a settling time. Settling time is the when the graph, the waves start to be like stay same phase, in same phase, settling time. So that's time when it's 455, that's the time. Then we're going to see about the rise time. So this is the rise time. So rise times will be when the graph starts to rise up. So it's 58.5 seconds. Okay. Okay. Figure 10, the output voltage response with the settling time, rise times, and also the overshoot. This one, the peak and play. Okay, that's all from me. Thank you.
I'm Nagoli Suresh. Today I'm going to explain the result for multisim part. The figure 11 DC to DC boost converter show the boost converter topology in multisim software. Now I will further with multisim. We are going to see the characteristic of this circuit. The input voltage we give the 12 volt, inductor 0.22 millihenry, and this is the diode, and capacitor 0.102 millifarad, and resistor 32.4 ohm, and the duty cycle is 33.33%. And this is the wattmeter we construct to run the transient analysis. Now I will run the transient analysis. This is the output graph. I just simplify for initial that suppose will be 12 volts, but there's something different which drops something 0.5 around, so the initial time the voltage charge more than the requirement we want, which is 18 volt, and suddenly drop at the time, and the wave going up and down. The difference between the maximum and minimum value will be increased following of time. Based on this graph, we got the rise time, which is different between 10% and 19% of the amplitude. The value we got is 336.91 microseconds. And then we further with the overshoot. Overshoot is occur graph show the maximum value. Based on the graph, the overshoot occur at the 1.631 millisecond with maximum value of 22.22 volt. Next, I will continue with the settling time. Settling time is a difference between the initial time and the time when it starts to become stable. Based on this graph, the settling time is 4.88 milliseconds. And then we further with the ripple voltage at stable stage. Ripple voltage will occur when the gap between graph becomes stable. At the stable stage in voltage ripple in difference was only around 100 millivolt. And the discussion of this project is, for this part of the project, the desired value of the components have been calculated to design a DC to DC boost converter circuit. There are only one set of calculated parameters for inductance L and capacitance C. The minimum input voltage and power from the range are used, which are 12 volt and 10 watt respectively. The L and C values for the each set are shown in the calculation segment. Before there is simulate, the value of the parameters needs to be chosen. The inductance that has been chosen is from set 1, which is L equals 0.22 millihenry. This is because the inductance from the set 1 is the highest value among the set in order to get the small ripple current value in CCM. Same goes to the capacitance value 0.0 102 millifarad capacitor is chosen from set to due to its the greatest value among the others to get the output ripple voltage. For switching frequency, there are few values that have been tried, but the final value that meets all the specification is 20 kHz. The conclusion of this topic is the boost converter is DC to DC power converter that steps up voltage while stepping down current from its input supply to its output load. For this operation, we use MATLAB simulation to find output voltage transient response, which is rise time, overshoot, and settling time. That's all from us. Thank you, sir.